This vodcast is going to cover the topic of Hess's law and to get you familiar with how to do Hess's law problems. Hess's law is named after Russian chemist Germain Henri Hess, who was a professor of chemistry at the Technological Institute of St. Petersburg in the 1800s. He published the law that bears his name in 1840 after studying the energy changes in a great number of chemical reactions. His law states that the amount of heat released or absorbed in a chemical reaction does not depend on the number of steps in the reaction. So in other words, if you go from reactant A to product Z all in one step, you will have the same total energy change as someone that went from A to Z in 7 steps. The energy from each of their 7 steps would add up to your 1-step energy change. If we put this in sports terms, the goal in hockey, let's say, is to score more goals than your opponent. It doesn't matter how many passes you need to take during any given play, as long as you get the puck in the net, that's what matters at the end of the day. Or in basketball terms, the goal there, score more points than your opponent to win a game. Doesn't matter how many times you have to pass that ball, how many dribbles along the way, how many times you have to get it from player to player, as long as it gets in the net and you score, that's what matters. Same with soccer. The idea there, get the ball in the net, score more points than your opponent. Doesn't matter how many times you have to pass that ball off to members of your team, as long as it gets in the net at the end of the day, what you're trying to do is score more points. Alright, enough of the sports talk. Let's try a sample problem. Alright, so you'll know it's a Hess's law problem because what you'll have is an overall reaction, which I like to call a puzzle box, and several pieces. So you'll have a reaction that you're trying to find the heat of reaction or the enthalpy of reaction for, and then it'll list several reactions that you can use to attain that goal, and those are the pieces. So those are listed below. First thing you do, label each stepwise equation, A, B, C, D, so on, if it's not already done for you. And that's going to help you keep track of the manipulations of these reactions as you do the problem. Alright, then, for the first reactant in your overall reaction, so in your puzzle box, find the stepwise reaction that has the same chemical and the same state of matter. So in our case here, we have nitrogen as a reactant, and we're looking for nitrogen as a reactant in the puzzle pieces below. And it's highlighted here, it's listed as a reactant there. Fabulous. It's on the same side. Now, if it wasn't, if it happened to be over on the product side, what we would do is we would flip it. What does that mean? Well, we would reverse the reaction. So we would put a negative sign in front of the C, and we would rewrite the equation by having the HNO3 as a reactant and the rest as a product. But we don't have to do that for this one because nitrogen's a reactant in our puzzle box, nitrogen's a reactant in our equation here, down here in C, so we just rewrite C down here, and then we're going to continue on. Alright, we're going to repeat this process now. We're looking at our puzzle box, and oxygen is the next thing that's listed. And, let's see, oxygen's in 2 reactions. Alright, if that's the case, what we do, skip it. Skip it for now, because whenever we do some other manipulations, that might get taken care of. So if you see that something shows up in more than one place, skip it and move on. Alright, so the last thing here we have is N2O5, dinitrogen pentoxide. It's a product. Well, we see it over here, but it's a reactant. This is a case where we need to flip it. Alright, so here's what we do. We write the 2HNO3 as a reactant, and then the dinitrogen pentoxide is a product, and water is a product, and we put the negative sign in front of the B to remind ourselves, hey, we flipped that. This negative sign will be important later on. Okay, so far we've used reaction C and reaction B. Now let's see. Use any unused stepwise equations to get rid of unwanted things. Putting them on opposite sides will allow them to cancel. Alright, well, what's an unwanted thing, you may be wondering. Well, if you look here in reaction B, we have water that shows up. But water is not in the puzzle box. That's an unwanted thing. So we look and we say, okay, well, we haven't used reaction A yet, and water is in reaction A, and it's listed as a product. The neat thing about Hess's law is if you have something on the reactant side and on the product side that's the same, it'll cancel out. So if we can get this over on the reactant side, we will be able to cancel out the water as a product, and it will be bye-bye unwanted thing. Alright, so what we do is we flip it, and we show that by writing the negative A, and rewrite the equation so that water is a reactant, and that reaction is going to be as listed here instead. Alright, so now we're going to begin to cancel things out that appear on both the reactants and product side. The goal is to add up all the stepwise equations to equal the overall equation. Multiply equations by a whole number if you need something more to match the overall reaction, or fully cancel something out that you don't want in the overall reaction. So our overall reaction has 2 nitrogens in it, and C only had 1. So I'm going to multiply the entire C reaction by 2, which is reflected down here. So we have 2 N's, 6 oxygens, 2 hydrogens, 4 nitric acids. Looking at our reaction B, there was only 1 dinitrogen pentoxide, but we needed 2, so I multiplied that whole reaction by 2. Alright, so the goal here is to get everything to add up. Let's see if it does. Alright, so what I'm going to do is I'm going to start with my first reactant with my first listed reaction here and see what happens. So I have 2 N2s, and I'm going to look at every single reaction, every single line, and see if I see N2 anywhere else by itself, and I don't. So what that means is that 2N2 is going to come down as a reactant, and I'm going to move on to the next thing. Alright, 6O2. Alright, so now I'm looking to see if I see O2 anywhere else. And aha, I do, right there. There's an oxygen here as a product. So what's going to happen is this O2 is going to cancel down here with one of the O2s up here. So we have 5 O2s now. And I'm going to bring that down as a reaction. Alright, how does that look for my puzzle box so far? 2 N2s, 5 O2s. Okay, awesome, that's good, we want to see that. Alright, now let's move to the next thing. We have 2 H2s. Alright, that's a reactant, but I don't see that in the puzzle box, so let's hope it cancels somewhere, or else we have to keep looking. Do I see H2 by itself anywhere else? Ah, yes I do. Aha, and it's a product. So 2 reactants, 2 H2 there, cancels. 2 products, H2 cancels. Yes. Alright. A product of 4HNO3. Alright. Do I see it anywhere else? Oh, there's 4HNO3. And nowhere else. Okay. Product cancels reactant. Nice. Alright. Now we have N2O5. I'm going to switch colors so it's easier to see. There we go. We have 2 N2O5. Don't see it anywhere else. That's good because in our puzzle box, dinitrogen pentoxide is, in fact, a product. Alright, and now we have 2 waters and 2 waters. They're on opposite sides of the arrow, so they cancel. Perfect. We have what was in our puzzle box down below. So now the reactions are complete. Next up is we actually do some math. Alright, the reason why you're keeping track of what you did is so now we can look at the heat of formations here. So we have 2 times C, and C is negative 74.1 kilojoules. And then we have 2 times the opposite of B, so 2 times the opposite. Aha, I have a typo here. See, this is why we need to check ourselves. A negative and a negative. Alright, so that will be positive. Okay. And then the last one here is we did opposite of A. Well, that means it's going to be a negative negative, which will end up being positive. Alright, and we add those up together and we'll get the heat of formation for this reaction. And this one ends up being 576.6 kilojoules. And the sign is positive, which means this is an endothermic process. so it will take in energy to do this. All right? Okay, now I want you to try this one, and I'm going to have the steps kind of listed out screencast style, so pause this every once in a while and see if your work checks with mine. One thing I want to point out is I was typing this too fast, and this heat of formation here should actually be negative 3536.6. So, all right. Pause this and see what you get, and then check it. All right, do a check here. First reaction, carbon is a reactant. Reaction A, carbon's a reactant. Write it down as is. Second reactant, hydrogen, reactant. Hydrogen's a reactant in B. Third reaction, pentane is a reactant rather than a product, so you need to flip. Then you start to add things up, and you look for carbon. Carbon's a reactant, but there's only one of them. You need 5. Multiply everything in that reaction by 5. Next reaction, hydrogen. It's only found in that reaction B, but you need 6 of them. So, multiply everything by 6. That gives you 3 O2s. Pentane, there's only one of. Good. Alright, so now we go into checking things meticulously here. Alright, so we have 5 carbons, that gets pulled down. So we're done with that. Oxygens, 5 oxygens, 3 oxygens, that's 8. 8. They cancel. Nice. Alright, more reactants, and we have 6 hydrogens. And we have 5 CO2s. 5 CO2s. They go. 6 waters. They go. And then we're left with pentane. Alright. That's taken care of. Now we do the math. Alright, so this enthalpy of reaction is negative 145.7 kilojoules, which is exothermic. That's what that negative sign means. There you go. We've done a couple Hess's Law problems. Hopefully that will help you in being prepared for doing these in class over the next few days. See ya!